Hey everyone, today we're going to pull back the curtain on a secret rhythm that's hidden all around us. It's in the tick-tock of a clock, it's in the shimmer of a light wave, it's even in the hum of a tuning fork. It's called simple harmonic motion, and it's one of the most basic, fundamental patterns in all of physics. So let's see how it works.
All right, to kick things off, we're just going to look at a few things that swing and vibrate and repeat. You see this stuff every single day, but what you might not have realized is that they all share this deep, kind of beautiful mathematical connection.
So what is that connection? I mean, they're all oscillating, right? They're all doing this predictable back and forth dance. But the real answer, as we're about to find out, actually has less to do with swinging back and forth and a whole lot more to do with just spinning in a circle.
Okay, now let's get to the really cool part. Let's reveal the beautiful and surprisingly simple idea at the heart of all this. It all begins not with a swing, but with a spin. Check this out. This machine here is basically the key to our entire story. You've got a wheel turning in a perfect, smooth circle, and it's driving that piston up and down, up and down. That simple, repetitive up and down movement is the whole secret. Think of it like this. It's the one-dimensional shadow of a two-dimensional circle. And there it is. Our source material gives us the big definition. This very specific kind of to and fro motion, the kind you get from perfect circular motion, has its own special name. See, this isn't just any random wiggling around. It's a very precise and predictable pattern. And wow, this diagram just illustrates the whole idea brilliantly. This is the master key. Seriously, on the left, you've got our point just moving in a circle. But on the right, we're tracking its vertical position, its shadow, if you will, as time marches on. And what do you get? A perfect, smooth wave, a sine curve. Let's break down exactly how we get from that circle to that wave.
First step, just focus on the circle. Picture a dot spinning around and around at a perfectly constant speed. Nice and easy, nice and smooth.
Okay, now for step 2. Forget about the spinning for a second and just watch the shadow that dot would cast on a wall. That shadow doesn't go in a circle, does it? Nope. It just goes straight up and straight down. It actually speeds up as it goes through the middle, slows down at the top, stops for just a split second, and then does the exact same thing on the way down.
And here is the big reveal. If you could pull a long piece of paper sideways while that shadow does its thing, it would trace out that perfect wave. That wave is the visual signature. That shadow's dance is simple harmonic motion.
So now that we have that picture in our heads, we can finally tackle the formal physics definition. I know, it sounds a little complicated, but it's really just describing what our shadow does. It's always trying to get back to that center point, and the farther away it gets, the harder it gets pulled back. This little equation right here, A equals negative omega squared y, well, that's the secret rule, the mathematical code for SHM. A is the acceleration, that's the pull back to the center. Y is the displacement, that's how far you are from the center. So the equation just says the further out you are, Y, the stronger the pullback, A. And that minus sign, it's absolutely crucial. It means the pull is always in the opposite direction of the displacement, back towards the middle. That omega squared, that's just a constant related to how fast our original circle was spinning. A faster spin means a stronger pull and a quicker oscillation. Okay, so we know what simple harmonic motion is. Now let's learn the lingo, the language physicists use to describe it. And don't worry, we're going to keep using our spinning wheel analogy to make it all crystal clear. We are back to our master diagram because literally everything we need to know about the wave is already encoded in the circle that generated it. The size of that circle, how fast the dot is moving, it all maps directly onto the properties of our wave. First up, amplitude. It's just a word for how high and low the wave goes, its maximum distance from the center. And in our analogy, it couldn't be simpler. The amplitude is just the radius of the circle. A bigger circle makes a taller wave. That's it. Next up is the period, which we write with a capital T. This is simply the time it takes for one complete cycle. You know, for the shadow to go from the very top down to the very bottom and all the way back up again. And in our analogy, it's just the time it takes for our dot to make one full trip around the circle. And finally, that brings us to frequency. Now, if the period is how long one cycle takes, frequency is how many cycles happen in 1 second. They're just two sides of the same coin, right? So if the period is, say, half a second, the frequency is 2 cycles per second, or 2 hertz. They're just the inverse of each other. So the shadow dance is a really neat idea, but why is it so incredibly common in the real world? Well, it's because nature is full of systems that are stable. Anytime you push something away from where it wants to rest, like a pendulum or a spring, there's a restoring force that tries to pull it back. And super often, that force behaves exactly according to our secret rule. Let's look at two of the most classic examples. On one side, you have the pendulum, the heart of every old grandfather clock. On the other, you've got a mass just bobbing up and down on a spring. They look completely different, but as we're about to see, they are both playing by the exact same secret rule.
Let's start with the pendulum. Now, there is one little condition. This only works perfectly for small swings, but as long as that angle is small, the force pulling the pendulum back to the center is directly proportional to how far away it is from the center. Hey, that's our rule. The pendulum is doing the shadow dance.
And this leads to a fantastic bit of history from the source. The story goes that Galileo was sitting in a cathedral and he noticed a lantern swinging back and forth. He used his own pulse as a stopwatch, and he discovered that the time for each swing, the period, was always the same, whether the swing was big or small. He was the first one to decode this fundamental property. Pretty cool.
Okay, now for our second example, the mass on a spring. And this one is even more direct. Because of something called Hooke's law, the force that a spring pulls back with is always proportional to how much you stretch or compress it. It's a perfect, real-world example of that restoring force that defines simple harmonic motion.
So we got this perfect, beautiful, repeating motion. But if you've ever pushed someone on a swing, you know you have to keep pushing, right? In the real world, things don't just swing forever. So what's going on? What gives? This slide just shows it perfectly. On the left, that's the ideal free oscillation we've been talking about, where the amplitude just stays the same forever. On the right, well, that's the real world. Forces like air resistance or friction are always taking a little bit of energy out of the system. We call this damping, and it causes the amplitude to slowly shrink until eventually the motion just stops.
So from the swing of a simple pendulum to the very light that's letting you see this screen right now, this elegant dance of a shadow cast by a spinning wheel is a truly universal pattern. And that kind of leaves us with a final thought. Where else is this fundamental rhythm hiding in our world, just waiting for us to notice it?